Welcome to this video lesson. In this video, we will be looking at the basic concepts of energy in simple harmonic motion. In the last video, we looked at the kinematics of simple harmonic motion. So we looked at position, velocity, and acceleration. Today, we'll be looking at potential energy and kinetic energy. So an object at this moment in time is at rest. So this is when we pulled it all the way to the right and we're trying to let it go. Since it has no motion, kinetic energy for this would be 0 at this point. For this specific case, we got a spring, and spring energy comes from the deformation of the spring and is fully stretched at the moment, so fully deformed, and therefore is going to have some potential energy. I'm going to write max. As the object moves in this direction, it gains some speed, and once it reaches this position, so here it's the force acting on it is to the left and it's moving to the left, so it's speeding up. Even though the acceleration is decreasing over time, it's still accelerating and therefore still speeding up right to this point. And right after this point, it's now moving to the left, but now it's being accelerated to the right because the spring is now compressed and therefore it's going to slow down. So at this point over here, it's going to have this max velocity and therefore max kinetic energy. Same thing for potential energy. In this case, it's no longer deformed at the equilibrium position. It's not stretched and it's not compressed. When it reaches the end point, it is fully compressed, meaning it's fully deformed, and therefore it's going to have max here, but it has no velocity. When it reaches the equilibrium point again, moving backwards, it gains speed because we have the force acting to the right. It's moving to the right, so it's speeding up to this point, and then right after this point, the acceleration starts becoming in the negative direction while the object is moving in the positive direction. It's going to slow down. So max velocity always happens right at the equilibrium position, and therefore this is going to be max and no deformation here, so this is going to be 0. Again, now it's moving to the right, it's slowing down, so it's losing its kinetic energy. So the kinetic energy actually decreases at this point, and it reaches a value of 0 right here. And the potential energy, because it's fully stretched, fully deformed, this is going to be max. So in terms of what's happening in between here, I'm not going to write minus or positive. Kinetic energy can't really be negative, but it's increasing to a max because it's gaining speed, and potential energy is decreasing because the deformation of the spring is becoming less. And at this point, it's slowing down, but deformation is increasing. So potential energy increases, but kinetic energy decreases. At the very end point, it's got 0 motion, so 0 kinetic energy, but it's accelerating to the right, meaning that it's going to speed up, but the deformation keeps decreasing, and therefore this decreases. And then from max, this one decreases to 0 as it reaches a 0 speed and slows down, while the deformation, it's becoming more and more stretched and deformed, and therefore potential energy increases to a max. Okay, let's graph this versus time, and let's make sure we understand the ideas here. So just to label the timing here, right at the very beginning here, let's say time here is 0. And the entire period or entire oscillation happens from here all the way back to here. So this is one full period. Halfway there is 1/2 of a period, so that's right here. And between those, we got 1/4 of a period, and we got 3/4 of a period. Okay, so in this specific case, the starting point is the max position over here. So this is at an amplitude, meaning we got maximum potential energy but 0 kinetic energy. So I'm going to use 2 different colors here. I'll use purple to indicate the kinetic energy. So this starts here, so EK. going to be purple. I'll use pink for the potential energy. So this is going to be at some max position over here. Kinetic energy is going to be increasing up to a max at a quarter of t. So at this point over here, once we reach the equilibrium position, we're going to have max kinetic energy. And then at half an oscillation, we go back to 0 because it's now fully compressed and it's at an amplitude or at rest, and then it speeds up again and it slows down again. So that's the idea here. For potential energy, right at the 0 time, we got max, and then it reduces because deformation gets less and less, and we get to a 0 point here, and then the deformation starts to increase again, and we increase our potential energy, and then we reach a 0 again when it reaches the equilibrium position because it's no longer stretched or compressed, meaning it's got 0 deformation, and we got max deformation at this point. Now this somewhat follows a sinusoidal looking curve, so I'm going to draw this as such. I'm not doing a perfect job, but it gives you the idea. Again, you need to know conceptually what's happening at different points, because here the starting position is at an amplitude, and if it wasn't at an amplitude, if we started at an equilibrium position, we would have maximum kinetic energy in the beginning, and we would have 0 potential energy at the beginning. So you need to pay attention to when things are happening, and I'm almost finished this lovely graph. Okay, there we go. Now, one other idea that you do need to know about this is total energy, and I'm going to write this out. And total energy is equal to the kinetic energy plus the potential energy. And I'm going to just box this equation. And what this means that at any point, if you add the potential energy and the kinetic energy, that will give you the total. So if I add them together, 0 with this, whatever this value is, I'm going to get a value right at this point. I got 0 and a value here again, 0 and value again, 0 and 0. In the middle points, when I add this half and this half together, I'm going to get a value there as well. And here again, because we're assuming that the total energy, there's no loss of energy anywhere, it means that the total energy remains constant, and that's important. So ET remains constant here because we're not losing any energy. So whenever there is a decrease in kinetic energy, potential energy increases. And whenever there is a decrease in potential energy, kinetic energy increases. And that would mean that kinetic energy is always converting to potential energy, and potential energy is always converting to kinetic energy. In terms of position, whenever the object is at its maximum position, it's got no kinetic energy at all, and this is always the fact because it's not moving, and it's got maximum deformation on the stretch, so it's got maximum potential energy. So we got no kinetic energy, but we got lots of potential energy. Right at the equilibrium position right here, or these 2 points, we got maximum kinetic energy because the object is moving at its maximum speed, but we got no potential energy because the spring is not stretched or compressed, meaning that there is no deformation at all. So at this point, there is none of this, but there is lots of kinetic energy. Just to make this simpler, I'm just going to draw a straight line which represents the total energy, and the total energy here never decreases. So this is going to be my ET as before. I'm going to have my kinetic energy, and I'm going to have my potential energy. So my potential energy, again, right at the center, there's no deformation, so it's 0. Back, and when the position is now at a negative maximum position, right here, we have no kinetic energy again because the object is not moving at that instant of time, and the potential energy is at a maximum. So I'm going to go ahead and put a dot right here, and I'm going to put a dot right here. Now we'll draw the curves for this so you can see that as well. We'll come up with the equations for these a little bit later on, so you'll see how the equations work in a separate video. But conceptually, you need to know that what happens to potential energy and what happens to kinetic energy at different positions, and at different times. Okay. Just before we end the video, there's one other main idea that we need to know, and that's how does the energy, the total energy, change, and what is it dependent on? One of the ideas is that the energy in simple harmonic motion is proportional to the mass, and you can think of this as this. Whenever you change the mass here, there needs to be more energy in order to move it back and forth. So you can, if you're trying to provide energy to a simple harmonic motion, in order to move it with the same frequency or the same period and the same amplitude, if you increase the mass, you need more force. And therefore you need to put in more energy in order to move it back and forth for a heavier object. And that energy, because the mass is larger, more energy is required. The other factor is the frequency. So energy is actually proportional to frequency squared, meaning that, okay, if we have the same amplitude and the same mass and we're oscillating it every 1 second, if I want to oscillate it at half the time or twice as frequency, I need to put in a lot more energy into it, and a lot more energy. So that would mean that if I increase the frequency by a factor of 2, or period divide by 2, then I need to increase the energy by a factor of 2 squared. So if I need to increase the frequency by a factor of 3, I need to change energy by a factor of 9. Lastly, the idea is that energy in simple harmonic motion is proportional to the amplitude squared. So the idea is such that if I have the same frequency, so if I'm moving it back and forth in 1 second, and I have the same mass, but then I increase my maximum amplitude by a factor of 2, then I have to, if I want to keep the same frequency with the same mass, I need to put in a lot more energy. Again, if I put 2 times if I increase the amplitude by a factor of 2, I need to put in 2 squared, or 4 times the energy, in order to keep it at the same frequency or get it going at the same frequency. With this one, you can also think about it in terms of springs, because if you move this, let's say this much, but if you want to increase the amplitude by a factor of 2, that would mean that you got to put in about 4 times the energy, because the force is increasing and increasing and increasing, and it's becoming harder to actually pull this twice the amplitude. So you actually do need 4 times the energy to move the objects twice the amplitude. But I like to always think about it in terms of concepts. So as mass increases, you need to put in more energy in order to oscillate that mass. If you want to increase the frequency, so going faster, you need to put in a lot more energy. And if you need to increase the amplitude but keep the same frequency and mass, you also need to put a lot more energy in order to move the objects. I hope that gives you a little bit of conceptual ideas about simple harmonic motion and energy. We're going to cover the equations on another video. Have a wonderful day.